All right, part 2 of acids and bases. I talked a little bit at the end of the last set of notes about the Arrhenius acids and bases, and the definition basically is just, that acids start with a hydrogen and bases end with an OH. But this isn't a great definition if you're trying to classify things, maybe a little bit more concisely instead of using two separate ions to identify things. This is where pH comes from. pH and POH. We'll talk more about that on the actual pH notes. But that is where these calculations come from. Then you've got the definition that we're going to use most often in this class, and I say most often, I know we only have like 2 days of class left, but, and when you get into AP Chem, this is the definition that we use the most. The Bronsted-Lowry definition emphasizes the role of that proton, that hydrogen ion. And basically it says that the acid donates the proton and the base accepts the proton. And so if we stick with that baseball analogy that I started in part 1, and in that the acid is the pitcher, the hydrogen ion is the ball, and the base is the catcher, who is at home base. That's pretty funny, right? The pitcher will actually pitch the ball to the base. So the acid is always the guy who has the ball. If you have the ball in the form of the hydrogen ion, then you're the acid. If you're going to be accepting that ball, if you're going to be catching that ball, then you're the base. So coming down here and looking at this, if you look at your reactants, you say, okay, who has the ball here? Well, they both have hydrogen, so you got to look on the other side. Who got rid of the hydrogen? Who threw their hydrogen away? Well, if you see, chlorine is now missing a hydrogen, so that makes the HCl, hydrochloric acid. That's your acid. And since on this side, the water is what caught the hydrogen, that makes the water in this case a base. Water is a very special molecule we'll talk about specifically in a second. But so that's how you can tell which one's the acid and which one's the base. Who's going to be throwing, who's going to be catching. So just a little bit of practice in that. Obviously we just did this one. There is one thing that I need to mention. The hydrochloric acid is the acid, and in this case the water is the base. But why don't we classify these guys over here on this side? Well, we can't just call them acid and base, because then it might get confused with this acid in this base. And if I asked what's the acid in this reaction, you might go, well, do you want the acid on this side or do you want the acid on this side? And so to clarify that, the solutions do still have acidic or basic properties, but instead of just calling them acid or base, we call them conjugate acids and bases, because the word conjugate means to go with. And so like the conjugate base would be what goes with the acid, and the conjugate acid would be what goes with the base. So the conjugate acid is what's left over after the base accepts the proton, and the conjugate base is what's left over after the acid donates the proton. So here's our acid, HCl. After the proton has been donated, the proton is gone, what do you have left? Well, you have chlorine ion, so that makes him the conjugate base. And then the guy that has accepted or caught the proton becomes the conjugate acid. And the reason that this works like this is because if you think about it, on this side of it, remember the acid has the hydrogen to throw, to pitch, and the base has the ability to accept it. So now this water molecule has the extra hydrogen on here that it would love to pitch right back to the chlorine. In this case it won't, because hydrochloric acid is a very strong acid. And so it is going to have the unidirectional this way. But if it was, an equilibrium kind of acid-base reaction, then, it would go back and forth, and it would just be like, playing a game of catch in your backyard or something. So to practice on this a little bit, if we had ammonia and water giving us the ammonium ion and a hydroxide ion, which one's the acid, which one's the base, which one's conjugate acid, and which one is conjugate base? So let's look at this first guy, NH3. Well, what happens to him on the other side? Looks to me like he accepted the proton. He caught the ball. So the guy that does the catching is the base, which means the guy that does the pitching, the guy that lost the hydrogen on the other side, so notice he's got one less hydrogen than him, that makes him the acid. Then on the other side of it, the guy who did the catching, who has now caught the ball. Remember, whoever has the ball is the acid. So whoever caught the ball is now the conjugate acid. And the guy who is ready, or who doesn't have the ball anymore because he threw it away, is the conjugate base. So I'm going to pop up another one here. I want you to try to do it on your own and then hit play when you're ready. We've got phosphoric acid plus water, basically the ionization of phosphoric acid. And it's just going to lose one proton, send it over to the water. So in this case, the H3PO4 was here. Over here, it has lost a proton, so that means it pitched it away, it threw it away. So that means the H3PO4 is, oops, I don't know why that popped up like that. That's the other reaction. We'll do that one in a minute. Let's see if this comes up right. No, it's not going to come up right at all. Sorry. So we'll just do this one first. So H3PO4 is the guy that threw the hydrogen, so that makes him the acid, which by default makes water your base. And then over here, what is left over after the acid has gotten rid of the hydrogen is your conjugate base. And what's left over after the base has accepted the hydrogen is your conjugate acid. Coming down here we have Cu. This is the acetate ion plus water, giving way to acetic acid, you know what this is, and the hydroxide ion. So starting on this side, what happened to this guy? He was Cu with a negative sign, and now he has accepted the hydrogen. So whoever accepts the hydrogen is the base, and what's left over after the hydrogen has been accepted is the conjugate acid. Then, by default, if this is the base, then water now has to be the acid. If you look over here, water has in fact lost a hydrogen, so he's the acid, and he is the conjugate base. Now notice this. Water went from being an acid in this reaction, to a base in this reaction, to an acid in this reaction. Water sure is special. Okay, I don't know what's going on with this, so we'll just go to the next slide here. Water is a very special compound called an amphoteric compound. And that's a compound that can basically go both ways. It can either donate a proton and be an acid, or it can accept a proton and be a base. And water is a perfect example of this. Anything that has a hydrogen and a negative sign, like HSO4 minus, can be amphoteric. H2PO4 minus can be amphoteric. HPO4 minus can be amphoteric, because all of these guys have a hydrogen that they could donate, which would make them an acid, or because of this negative sign here, they'd be more than happy, well, this one wouldn't, they'd be more than happy to accept a proton and, not be negative anymore. So an amphoteric compound is any compound that can go both ways, and what direction it goes is all dependent on what it's with. It's all a relativity thing. So if water, coming back to this one, if water is with a base, well then water is going to appear acidic. If water is with an acid, then water is going to appear basic. I don't have time to wait for that. Last definition I want to give you, you do not need to know the specifics of how to find them, how to work it out, or anything like that. I just want you to recognize the Lewis acid base definition was done by Gilbert Lewis. It is the broadest definition of acids and bases, and it emphasizes the role of the electron. It's basically the exact opposite of a Bronsted-Lowry definition. Bronsted-Lowry says the acid donates a proton. Well, here the acid accepts an electron, and the base donates the electron pair. And like I said, you just need to know that it focuses on electrons, that the acid accepts the electron pair, and the bases donate the electron pair. Beyond that, you don't really need to know any more than that. In AP Chemistry, we get into it a little bit more. It deals with the whole Lewis structures, if you remember those things with like the dots and dashes to, show rough molecular shapes. But beyond that, I don't expect you to know the specifics of it. So that's all I got for our first part of our acids and bases notes. I'll do one more set of notes on pH, and that'll be it.